All right, welcome. There's no conference complete without an AI talk, so let's end the day one strong with an AI talk. So we're going to talk about something that doesn't usually get the deserved attention in the AI infrastructure discussions, which is we're going to talk about storage. So my name is Tushar Gohad. I'm a senior principal engineer at Intel. Been associated with Ceph since 2015 and continue to. I worked very closely with Kyle.
Hi, Kyle Bader. I work IBM Storage, Chief Architect Data and AI for Ceph. So how many of you here have used ChatGPT, Anthropic, interacted with a chatbot of some kind? Nobody. OK. Let's see here. All right, so what is inference and KV caching? Well, if you think about the simplest example, it's when you send a prompt to the LLM, it needs to break things down and do two fundamental steps. And those two steps are prefill. So it takes your prompts, and then it calculates the KV data for the tokens that you've presented. And then it needs to do the decode. And the decode is the part of the autoregressive model that generates the output tokens, that is the response. And as the prompts start to get larger, the necessity for KV caching really goes up. So as two kind of examples, if you take like the classic attention is all you need paper, that weighs in at about 8,000 tokens. If you take the paper that was published by the IBM Granite team for Granite 3, that's about 30,000 tokens. So that gives you kind of a small idea of the scale of the number of tokens. And if you're doing prompts where you're providing artifacts, maybe several documents, you can see how this really drives up the context length. And you'll often see this with retrieval augmented generation type workflows, but also summarization workflows, or even if you're just having a long chat with a LLM where there's multi-turn conversation and there's a lot of previous context that needs to be incorporated into the response. So of the two portions, you have this prefill portion and you have this decode portion. The prefill portion, because it knows all the tokens that are associated with that prompt, it's very easy to parallelize across the different GPUs that you have available. On the other hand, the decode part is there's a very high computational overhead because it needs to generate the next token, and then it needs to update the weights across all those layers, and then kind of iterate through one token at a time. It can't parallelize well. But one of the things that we can do on the storage side of things is we can save the results of this prefill. And this is really important because the computational complexity of the prefill operations is quadratic. So as the number of tokens increases, so as the sequence length gets longer, the amount of work that you have to do to generate those KV pairs is nonlinear, right? So it gets worse and worse and worse at a quadratic rate. And that's because it's updating the weights across this kind of ever-growing matrix. So if you think of a matrix where it has the tokens across the top, and then you have the tokens going down across the bottom. Every time you add another token, you're adding a row and you're adding a column, and so that's where this complexity comes from. So if we were to save these matrices, if we were going to save all this KV data, what would it look like? And the utility that we've been using in order to persist the KV caches is a tool called LM cache. And in LM cache, the default cache block size is 256 tokens. And the first thing when I'm looking into the LM cache and how it does KV cache blocks, I see that the size of the cache blocks is tokens, and I go, well, I don't know what that means in terms of storage capacity. And it actually is variable based on the architecture of the model. So I won't go into all the details here, but there's a lot of different things about the hidden size, the number of KV value heads, the head dimensions, and the precision of the model that impact the amount of KV data that you need per token. But for one example we have on here is for a Qwen 3 32 billion parameter model, you need about 62-ish megabytes worth of data for a cache block of 256 tokens. And then on here, there's a link to a KV cache sizing calculator on the LM Cache website where you can kind of, from a drop-down, pick a particular model, enter in the number of tokens for a cache block, and then it'll give you an estimated size.
So Kyle introduced the idea of context in a KV cache block. If you look at across various sizes of models, let's say Granite 8 billion, Llama 70 billion, or Qwen, there's a specific pattern that you'll notice, right? It's the relationship. So the y-axis basically shows the KV cache size, and the x-axis, if you can notice, that's basically the context length, which is essentially the context window that a model is capable of processing at a time. As the context window length or the window increases, you can see that the KV cache grows perfectly linearly. So essentially, if you double your context length, it means you double your memory requirements, right? And so in a moment, we'll talk about how this impacts some of the decisions, sizing decisions with respect to GPU memory versus the other tiers of memory. But essentially, just to give you some examples, right? So just to put things in perspective, so if you look at, let's say, a Llama, Llama model at 2 million tokens, and 2 million tokens is not uncommon. So if you look at, let's say, Gemini 2.5 Pro, it actually supports 2+ million token size window. So at that size, if you look at the KV cache growth, it's upwards of 640 gigabytes. Even a smaller, more optimal model like the IBM Granite 8 billion, even there, the size of KV cache is 288 gigabytes. So think about a limited GPU, I want to say a node with limited number of GPUs with limited HBM, and try to fit these sizes. So a typical GPU, for instance, an H100 has 80 gigabytes of HBM, or a Gaudi 3 has 128 gigs. So essentially, some of these sizes, as they're growing, there is a memory problem for AI inference. Now in a few slides, I'll actually show essentially like what how an HBM, what goes into an HBM, like when you're running distributed inference on the GPU. But essentially, this slide basically calls out the constraint that there is a problem essentially, which is a linear growth of KV cache with context length, and that we need to solve. So Kyle will introduce a couple of concepts, and we'll get back to the context length discussion.
Okay, so the real benefit to offloading KV data to storage is it enables a space-time trade-off. So, and in this case, I'm trading the time in terms of GPU hours for space in my storage system. And because there's a very high cost associated with the time spent on GPUs, it turns out that this is a very good trade. The other thing is I'm not just freeing GPU cycles in order to be able to use them for decode or be able to use them for pre-filling tokens that I haven't seen before. It can also speed up inference. And there's a couple different metrics that are used to express latency in the terms of inference. The first one is time to first token. So if we are able to retrieve cache blocks from storage faster than we could computationally generate those KV pairs, then we get a speed up. And that reduces our time to first token. There's another associated metric that's on the decode side that's TPOT, which is time between output tokens. And we're not focusing too much on that here. We're mainly focusing on reducing the amount of time before the model starts to output tokens back to you in terms of giving you a response. And so as long as we can load this data from storage faster than it can be computed, and remember that the cache data size is linear as the tokens get longer, whereas the work involved to computationally generate them is quadratic. So as the token, or as the sequence length gets longer, we have more and more time to complete this arbitrage and end up with a reduced time to first token. There are other tricks available to us too, because we can parallelize the fetching of these cache blocks. So we can fetch cache blocks in parallel. If it's a big cache block, we can use methods to read different offsets of that cache block in parallel, and further get more speed up by increasing the parallelism. Whereas in the computational path, you can't parallelize it as well in the same way.
So, so the discussion always comes down to, like, do you need, to think beyond HBM or the CPU host memory that you have available? Like, there are several blog authors on Medium that we had discussions with that continued to, say that, okay, we're not there yet where we need to think about HBM, and the CPU host memory, basically storage. So this is a slide to basically talk about the problem, right, and the scale of the problem. Essentially, just 2 years ago, the context lengths were 4 kilobytes, 8 kilobytes maybe. Today, as I said, it's about 2 million tokens. And if you look at what Sam Altman said in an interview recently, he basically has talked about context lengths of several billion tokens, right, when the model basically gets to know you better and better, more than probably yourself, right? So the billion tokens is not just a big increase, it's an exponential increase, it's a 5,000-fold increase, right, where the HBM and the host CPU memory are just not going to be enough. Now, the other issue, let's talk about the other challenges that come up, right, with this context length growth. So as the, basically the memory where the model stores all the previous tokens it's seen grows linearly with it. So more context equals more memory needed. So when you fill it up, let's say, so if you focus on the second bullet here, it's essentially saying that when you fill up the HBM, two bad things happen, right? First, you cannot run as many requests at once because you're out of memory. So you are leaving GPU cycles on the table when your memory starved. And then the second is there's something called a batch size, which is essentially how many tokens can you serve. So both concurrency as well as batch size that you can serve get impacted, and you leave a lot of GPU cycles on the table. And if you think about the cost of cycles, GPU cycles is the highest, followed by CPU cycles, and then you have the other things in the tier, right? So you have HBM, the CPU memory, and then storage in that hierarchy of cost. So essentially, this slide is basically to make a case for additional cache tiers that are more cost-effective, so that we don't have an out-of-space problem. Rather than having an out-of-space problem, let's turn it into a stream when you need problems. So more like Netflix, right? You don't download the entire movie, you stream it when you need it. By offloading KV cache intelligently, you can free up, essentially not just the HBM space. And HBM, by HBM, I mean the GPU VRAM, right? So by freeing that up, you free up those CPU cycles that are sitting idle, which means better hardware utilization, better MFU, which is essentially the model flops utilization, which stands for the ratio of like actual flops utilized versus the theoretical flops spec'd, right? So essentially it's a newer modern unit of measuring model performance and GPU performance, right? So to improve MFU and concurrency, KV cache offload becomes necessary. Now let's zoom into like where does all this memory go, right? Because you may say that, oh, I have an 8 billion parameter model. I'm going to need about 16 to 20 gigabytes of HBM. I've got 80 to 128. So where does the rest of the space go, right? So this is a view like of a single GPU, and so if you look at the massive dark blue chunk, that's your model weights. They're not going anywhere, right? So that's a fixed overhead. The green section, those are called input and output activations, the green and the orange section together, I would say. And they're all intermediate calculations that a GPU does when doing, when it's generating tokens, right? So let's look at what's left, right? So you've got your HPU graphs, right, which are essentially the blue, and then tiny bit of paged attention buffers. So the only thing you're left with is essentially the dark green sliver, which is the minimum KV cache that you need. It's not your ideal cache size. It's absolute minimum that is allocated by default, right? So here's the brutal reality, right? So inference already took away your VRAM, right, your GPU memory, before you even started thinking about scaling context length or caching prefixes during, let's say, a chat session, right? So there's no room to grow. So you want to, if you want to 10x your context window, you can't do it. Same thing with concurrency. You can't get more concurrent. So essentially, this is why offloading isn't just an option, or tiered cache is just not an option. It's a necessity. So essentially, we need to move the KV cache somewhere, right? So there are some solutions to this problem, like you guys may have heard of tensor parallelism, data parallelism, where what you do is I have this big chunk of blue, right, model weights. I split that into multiple GPUs, right? So this chart basically shows from the left to right, it shows tensor parallel levels 1, 2, 4, and 8, which stands for essentially 1, 2, 4, 8 GPUs that you sharded your model into. The challenge is that when you do this, that orange is fixed. Your KV cache and other overheads that you saw here, right? All of these overheads on the right, they have to be replicated on each GPU. So what you're left to work with is essentially a very small amount of memory. Again, this makes the case for another tier of memory, which could be CPU memory. But then again, CPU memory is also priced, right? It's a scarce resource. So that basically moves us to a shared storage as the solution. So let's move into that solution space real quick. So in the next few slides, we're gonna talk about some of the experiments that we did constructing an inference stack based on vLLM. So vLLM is a popular serving framework from Berkeley. It's one of the most popular frameworks. It's only 2 years old, but it's at this point probably one of the most widely used. In fact, Red Hat has a lot of investment in it. And then LM Cache is a KV block manager that sits between, it's a vLLM and a cache tier. Like, let's say, in this particular case, we use Ceph Rados Gateway, right, S3, as the backend. So to get into the details, I'll hand it over to Kyle.
So as we got into this, we started thinking about what sort of Ceph cluster we might want to build in order to optimize for very high throughput in the case of object. And we drew some inspiration from the AI clusters that were being constructed by Meta. And they're currently using a design based on their Yosemite v3 platform. And then specifically, they're using sleds inside that Yosemite v3 platform that are called Sierra Point, which is a single socket system with about 6 NVMe's. And so we started looking around at different hardware vendors that had something that was approximately close to this. But we did want to have a few kind of upgrades from the kind of Sierra Point platform, which was based on kind of an older Intel CPU. It was based on the Cooper Lake designs. And so we arrived and kind of just started working with Supermicro, who has a 2U system that has four nodes in it. Each are single socket Xeon 6. And in them, we put the Xeon 6 E-core variants. So these are the ones that have a low TDP. Actually, there's a mistake on here. This should be 250 watts. And 96 core, 96 threads. So each system in this 4-node 2U setup has 96 cores, 96 threads, so there's no hyper-threading, 250 watts per processor. We have 512 gigs of DDR, and then we have a 2x200 bonded link that we're using to run all the traffic over. And then there's 6 Gen 4 NVMe drives from Kioxia. And then this is all connected up to a 400 gig fabric that had 2 different GPU hosts on it. This is the Gaudi host that we were doing testing with. And so this is the X14 platform from Supermicro as well. And so it has 8 Gaudi accelerators in it and 2 monstrous Granite Rapids processors. And that was kind of what we were using for the lab. In terms of the Ceph configuration, so we deployed IBM Storage Ceph 8.1, and we did some tests with both 2+2 and 2x replicated pools. And then we're running about 1K PGs for the data pool, and then 64 PGs for the index pool and the non-EC pool. And then we did kind of the standard tuning things. For scaling up the amount of bandwidth, we deployed 4 RGWs per host, and then we used the new capability that we have in the RGW service to deploy what's called a concentrator. So that deploys an HA proxy adjacent to the RGWs, but that HA proxy is configured to only balance across the RGWs that are on that same host. So we have 4 RGWs and then an HA proxy sitting and listening on just port 80, and then in front of that, we're using HashiCorp console with Core DNS to do multi-response DNS. So when you do a DNS query for s3.example.com, in this case, it gives 4 A records that each are associated with the concentrator on each of those hosts. And we knew that if we found S3 clients that had the S3 CRT libraries in them, that when they constructed their connection pools, they would multiplex the connections across these endpoints, and that way we could drive the bandwidth to all the hosts in the system without introducing additional complexities of more sophisticated load balancing or kind of ramming all the traffic through a single HA proxy or something like that. So as a baseline performance test, we were using LBencho at 62 megs. We did the 62 megs because that's approximately the size of the cache block for a Qwen 332B model. And with this 2U 4-node cluster, we were able to drive 60 gigabytes a second to this cluster on the read path. And this is actually quite phenomenal. And this is from a single GPU host. So we have a single workload generator on a single client going over to the 4-node cluster and driving this level of bandwidth. And this was at 288 threads. Like I said, we have these preposterous, there's 2 Granite Rapids sockets, and they each have 144 cores and 288 threads. So we have tons of CPU available on the GPU host. And so just from that single client, we were able to drive a huge amount of bandwidth.
So let's talk about. Let's start with the I/O path essentially. So in the stack that we were previously discussing, the vLLM, LM cache, and Ceph YS3. This is basically the right path. So essentially, every cache block, like we talked about, is about each of those blocks that this array represents is essentially 256 tokens in the Qwen32B model that we exercised. And essentially, the idea here is that you're basically storing these in a content addressable format because you're hashing the blocks. So if you're sharing these KV cache blocks across multiple instances, inference instances that may be running on different nodes, they don't have to have the knowledge of that exact prefix. So they basically need to just say, okay, have you seen this hash, right? Just asks that to LM cache, which does there's no lookup table, giant lookup table to track every cache blocks. You're simply using a simple hash on our actual content, right? And that hash basically becomes the key, which is crush-like thinking, right? So what does this mean, right? There's no metadata database. There's no coordination required, right? So you essentially have a single shared storage, no single point of failure. So all the goodness that Ceph gives you, but for AI inferences use case. And of course, I forgot to say on the previous one that it's unbounded storage, right? So the HBM sizing issues that I talked about, those are eliminated with the introduction of shared storage. And this path essentially shows the read path, right, where model needs particular piece of content. You hash it, compute the S3 key, and then you basically can fetch it. So the important part is the beauty of this architecture is basically simplicity, content addressable reads, asynchronous fetching, right, from S3, and graceful degradation on cache misses, essentially. So there's no life cycle management required outside of the minimal that's provided by LM cache already.
Yeah, I would say that this is we actually looked at a couple different ways of persisting cache through vLLM, and some of the other ones were very like file-centric or block-centric thinking, where it was like you pre-allocate a pool of files or block devices, and then it records metadata about which cache blocks are in which files and are stored at which offset and how long they are. And then you have to keep track of all this information and coordinate between all the different vLLM instances, and they have to cache this so it can do it quickly. Whereas this approach, it's just taking a hash of the sequence, so taking a hash of basically the tokens, and then that is used as how it's persisted in storage. And then if you were to have something that is cleaning up or deleting things in the background, like say you set a bucket lifecycle and it expires some of the objects, it doesn't matter because you don't have to worry about that, having some sort of dangling reference and some sort of metadata that points to those cache objects that are no longer there. In this case, because it's content addressable, and because it just treats the object not existing as a cache miss and will then generate it computationally, it doesn't matter. You can delete things, you can delete cache blocks, and it doesn't impact things other than the fact that you have to recompute the KV states for them. So this is one of our. This is kind of like the big aha slide here, where the blue line that kind of is higher up on the chart, that's the amount of time that it takes to computationally generate the tokens. And in this case, this is with a tensor parallel 2 configuration, so this is with 2 GPUs. And even at 100K context length, we're able to realize this 5x time to first token speed up, which is fairly significant. And as the context length continues to grow, then these lines separate more and more. And so this is further illustrated by this slide here, where we used a different GPU host. So instead of using the Gaudi GPU host, we also demonstrated this with AMD Instinct accelerators. So the MI300X accelerators is a GPU host that has 8 of them. In this case, it's tensor parallel 1. And we grew the context length further out to 130K, and we were able to see a speed up of over 10x in terms of like reducing the time to first token by withdrawing it from storage. So that really flat, nice line at the bottom, that's the amount of time that it takes to the first token when we're pulling cache blocks up from this 2U storage system, as opposed to computationally doing them with the accelerators.
Yeah, so we have established so far that that there's a clear benefit to shared storage. There's a case for shared storage. Ceph fits the bill, has enough performance to make that quadratic computation linear, essentially by storing the pre-computed KV cache blocks. So what's next, right? So you guys may have heard of a project called LLMD, which Red Hat and Google started. LLM D stands for distributed. So distributed inference is a big theme where, like Kyle described earlier, there's a pre-fill and decode disaggregation, which has specific benefits to having not just mixing heterogeneous AI accelerators in an environment, but also basically matching the need with the capability, right? So for instance, there's some GPU accelerators that are better at pre-fill like computation, whereas some others like Gaudi, for example, they're optimized for decode part of the pipeline. So LLMD is an orchestrator that does KV cache-aware load balancing, as well as just regular load balancing as well, right, based on the load on the vLLM instances. So so our next foray in this environment is basically a pre-fill decode disaggregation in a heterogeneous environment, where we are trying to showcase both the benefits to the pre-fill side as well as the decode side by utilizing KV caching. Anything else to add?
Yeah, and we were working with some folks on the LLMD side to try to establish doing KV caching with remote storage like Ceph, and have that be like a well-lit path that's well tested and well documented, and land that into releases so that people can very easily deploy these sorts of setups. And the nice thing from the Ceph side is it doesn't require anything new, really, right? Like, we created a very special purpose, high throughput Ceph cluster, but other than that, we didn't make code changes. A lot of the work that we did was around getting the different components on the AI stack to work together, and we've seen really meaningful benefit in doing that without having to get into elaborate special purpose hardware or configurations or those sorts of things. So there's some additional areas to explore. We do want to look at exporting buckets or CephFS file systems using Ganesha, so doing like NFS over RDMA, which would potentially open up the path for us to do things like GPU direct type access for these KV cache blocks, and to drive some further efficiencies. But even without doing those things, there's a very substantial benefit in terms of reducing the time to first token for inference without those sorts of things. So, and we want to thank, like, Intel has donated a lot of equipment, and we've all been working together. Supermicro has been our host for the lab, and so we appreciate them working with us to be able to do this work. We're the last talk, so if anyone has any questions.
Do you use like multiple buckets, like if there are different files and tokenized, and it will be used in different paths per se, or like only one single bucket which will store all the tokens?
So right now it really expects you to point these things, or at least the ones that you want to be able to share cache blocks across to a single bucket. Although I do think it's interesting to potentially add some partitioning logic to the caches, perhaps based off of, like, when you fire up vLLM, one of the things it does is it provides an OpenAI compatible API. And if you look at the OpenAI APIs, one of the things that you can pass is a safety identifier. So one thing that I think would be interesting is if vLLM added support for the safety identifier and then use that to steer workloads into cache partitions, because then, because of the way that we're doing things, we could plug into the like SerDes functionality of the cache block, and then we could do like encryption of the KV cache blocks as they're streamed down or were pulled from storage, like on a per partition basis, and so you could increase the security of the storage of these things, because it's, you know, it is representing context and there's potentially sensitive data there, and so kind of getting into a zero trust configuration where all the data that's at rest is encrypted and meaningless basically on the storage side, but then on the, you know, all the decryption is happening up at the GPU host level, and so that gives you that separation of responsibilities.
Thank you.
Yeah.
So is this applicable for like a consumer-facing product like ChatGPT? Like, wouldn't that just be a endless amount of storage pools, or would these be like really short-lived object storage per session?
Yeah, so if you look at, I think probably the best example of this is if you look at Gemini. Gemini has two different types of caching. One is implicit caching, and you can think of that as being analogous to like the ACS functionality that's in vLLM, so it's kind of just like this automatic caching that happens, and that saves them compute and can mean that they can return responses to you faster. They also, in Gemini, they have a thing called explicit caching, where when you pass a request to Gemini, you can indicate that you want to save the result of this cache, and it actually becomes like a KV caching as a service thing, because what Gemini and what Google does is they charge you by a rate. I think it's about $4.50 per million tokens per hour. So it becomes like another service where people can choose whether they want to store these cache blocks, and then, you know, it's up to them to make the decision of whether the reduction in latency and the decreased cost associated with the token generation is worth the cost of storing those tokens for however many hours. So I guess I should say that when you're using cached, when you're using cached data, you usually have a discounted rate in terms of token generation. Mm-hmm. So if you pay for the cache and then you do explicit caching, and then you're paying for that cache, if you use that cache in your prompt,
Gotcha.
Then the amount that you pay for the generated tokens is reduced considerably. So you can, you know, then it's up to the people that are consuming the service to decide whether they want to make the trade-off.
Okay, so if there's a repeatable workload that some organization.
Yeah, right. So if there's a corpus of documents and you're going to have a lot of people asking questions about them, or if you have a code base and there's, you know, people are going to be asking questions about the code base, or you also see this just with prompt templating, where they have kind of the system prompt and they have a bunch of boilerplate that's repeated across a bunch of different queries, because it's kind of behind, it's behind some other system, and or some sort of agentic workflow. And so yeah, absolutely.
Thank you.
In fact, like if you look at these charts, right? Oops, I think they're not up. But essentially, the time to first token gains that we showed, like 5x to 10x, those roughly correspond to, if you go to chatgpt.com and look at the pricing, you will see that the cache tier costs 90% less than the like live token tier. So some of these numbers actually that we showed actually reflect in pricing. So they are in fact using cache like we described.
Yeah, so I'm actually kind of excited to see more people that are, especially kind of like these neo clouds, offering these types of services to where they can do like KV caching as a service. I think that that will become increasingly popular, and I think kind of Gemini's at the forefront of that, but I expect both model as a service providers and NeoCloud GPU as a service type providers to start having things like this to provide to their customers.
Yeah, I think the last answer kind of partially answered my question, but I was just wondering, is it common for the cache to be LRU, or is it usually more like application, specific caching decisions? And then the second part of that was just like wondering, do you know what sort of typical cache hit rates you tend to get?
So on the LRU side of things, when you're dealing with inelastic storage, so if you're just using the block device in a GPU host, or if you're storing KV caches in CPU memory or in GPU memory, then you necessarily have to have an eviction algorithm. In the case of an elastic storage, like using object here, there doesn't necessarily have to be any sort of eviction algorithm because you're just writing the storage. You can have some sort of like cleanup thing in the background, and then if you clean up something underneath the system, you don't have to worry about it actually doing eviction tracking, because if the cache block isn't there based off the hash of the sequence for that cache block, then it just treats it as a cache miss and it just generates it.
So you can kind of just decide how much cache you want, and it's a little bit more elastic. Is that right?
Yeah.
Okay.
Yeah.
And then as far as the hit rate, I guess that's also tunable based on how big your cache is.
It depends on how big your cache is and the exact queries that are hitting your APIs, and that's something that we want to explore. There are some traces that have been published through some of the recent papers, and we want to kind of take these setups and replay those traces to see what the cache hit rates and the reduction in time to first token are with these more realistic workload traces, as opposed to like these synthetic, just long document benchmarks that we're running.
Yeah.
Thanks for that.
Yeah, and in fact, we tested this in two modes. One is a truly random, that's truly synthetic, but then there's also an interleave mode where you basically have, let's say you have 3 users that upload 3 documents, and then n users upload n documents, right? And that pattern repeats. By the time you come back to let's say you have doc 1 through doc n, and then you have the same pattern repeating. By the time you come to doc 1, that is most likely evicted, which means you don't get a cache hit. But then with Ceph, when you have shared storage, you're able to show that, again, that there's some of that work not covered here that we are looking at. But essentially, when you look at, sharing a GPU, like between models, users, right? When you have even an LRU cache like this, right, with that's elastic, unbounded, you can serve more users. You can serve more models, right, from the same set of GPUs. That's where we want to get to, essentially, right? But even this prefill, which is a compute-intensive stage, right, of the whole pipeline, I think we've been able to show a good proof point, right, that 5 to 10x gain is nothing to sneeze at. So, yeah.
All right, I think we'll retire into the other rooms and come find us if you have more questions.